This obviously is an important topic. It's called fundamental. There are two parts to the theorem. The second part we've actually been using, and I think you'll find it quite familiar and natural when we look at it. The first part is a little different, so let's have a look-see. So basically what we're saying is let's let some integral equal a function. G of x is equal to an integral, but it's of a special form. Notice that the integral is set from some number to a variable. A, the lower limit, is some number. Any number, doesn't matter, positive, negative, or zero. The upper limit is some variable, and again, doesn't matter. It can even be a function of a variable. We'll get there real soon. Don't get hung up on the fact that the integrand is written in t. It could be written in any variable, even x, but then there would be some confusion with the alphabet, with the letters. So we just use t. So, although it's important to recognize that this theorem only works when we're talking about continuous functions on a closed interval, and that it's in fact differentiable throughout the interval, the big piece or big thing to focus on is here at the bottom. And at the bottom you see this little statement: the derivative is equal to the function. You know, the integrand is some function, and when we apply or think about the fundamental theorem now, we're going to recognize that if we take the derivative of the integral, we go right back to the function. G is an integral. We're going to take the derivative of the integral. It's going to take us back to the function. That shouldn't surprise us, because these two operations, the derivative and the integral, are inverses of each other. In other words, one undoes what the other has performed. So if we come along and take the derivative of an integral, we're going to find that we come right back to the function. So let's see it played out here in an example. Before we do that, I just wanted to throw up what is sort of old school, and it's the way we talked about it back in the day, maybe a little simpler. The derivative of an integral, and notice it's the same form that we were looking at from the book or above. The derivative of the integral takes us right back to the function. So let's see an example and see how it plays out. So let's say we're asked to differentiate the following function, and the function is called g, just like in the notation used in the book. And notice that it's of this form, that is, the lower limit is some number, doesn't really matter what number, the upper limit is set to a variable, and the integrand is t squared minus t. Well, we're going to say the derivative, by way of the definition, requires of us no work. All we have to do is take the integrand, put x in, and we're done. In other words, g prime of x, the derivative of this function g, is simply x squared minus x. So let's talk for a moment how it is that this works by, in a sense, doing it longhand. And let me just get this out of the way, and let's do it long-handed. And what do I mean by that? Well, let's start off by saying, well, let's take this integral, which goes from 2 to x, this integral that we've labeled as g, and let's think about what would happen if we actually perform the integration. That is, we took the antiderivatives And then we actually applied these upper and lower limits. So wouldn't we get x cubed over 3 minus x squared over 2? And wouldn't that be our upper? And then we'd come along and we'd put in the lower, and wouldn't we get 8/3 minus 4/2? And although I could take some time to restate this, I don't know that it's necessary. Let's just remember that this is what g of x is, and this is its evaluation. In other words, we've worked the integral out. So let's come along now and find the derivative, because this is what this is about, right? Taking the derivative of the integral. If we perform that activity, wouldn't we in fact get 3x squared over 3 from the first term, which would simplify to an x squared? And wouldn't we get 2x squared, 2x to the first, excuse me, over 2, and wouldn't that simplify to x? And then isn't everything left a constant, and when we take the derivative, right, it would go to 0? So what have we got there? We've got the derivative is x squared minus x. Isn't that what the fundamental theorem told us with no work? So here's another example. This one is a little bit ugly. And let's say that the instructions were for this one to find, let's get the pen going here, to find g prime x. G prime, come on now, I can do this, g prime x. Well, because it is of this special form, we're going to say no problem. The answer is g prime x. We are in fact looking at it. Isn't it e raised to the 2x cosine squared 1 minus 5x, and we're done. Isn't that nice? Now, this is a pretty ugly integral. So for us to go off and work it out and then come back to that answer and take its derivative to prove this true would be difficult, and in fact it's unnecessary, because this derivative is what we said by the fundamental theorem. So if there's ever a doubt as to why we can say that, we'll just say it's by the FTC. It's by the fundamental theorem. Take a look at yet another example. Now this next example, I made it almost like the first one, and the significant difference is that I've switched up the constant and the variable in the limits of integration. So this particular time, let's say that we were asked to find, this time, h prime x. Well, it would require just a little manipulation on our part, or a recognition that going from x to 3 is the opposite of going from 3 to x. So this is e to the 2t cosine squared 1 minus 5t dt. This is still h of x. The only thing I've done is I've switched the limits of integration, and if I do that, it just makes the answer opposite. So these two steps sort of undo each other and keep it equal to h. But now it's of that form or flavor that allows us to take the derivative. That is to say, h prime x equals, and now we can say, well, it's the opposite of e to the 2x cosine squared 1 minus 5x. And that's it. That's by the fundamental theorem. So let's look at yet another example, another related example. So this final example is much like the previous two. I haven't changed the integrand. All I've done is messed around with the limits. So this time I don't have it from 3 to x. I don't have it from x to 3, but rather I've taken and messed it up in a sense by going from 3 to not x but radical x. And our instructions here would be much the same as the previous ones. This time the instructions would say find j prime x. So j of x is given. Let's talk about j prime x. And what we do here is we employ what is the chain rule. We say, well, we've got from 3 to whatever, so we're going to put whatever in. So it's going to be e to the 2 radical x cosine squared 1 minus 5 radical x, and then we're going to multiply by the derivative of the whatever, in this case the derivative of radical x. So our final answer here will be e to the 2 radical x cosine squared 1 minus 5 radical x, and now that derivative, that's x to the 1/2. So isn't it going to be 1 over 2, and you might want to say x to the minus 1/2, or let's put it in the denominator, x to the 1/2, or perhaps radical x down there. So that is j prime x. Let's do one more example and then we'll be done. Now I didn't want to take you too far too fast, so I have this one still written in t, but notice I don't have the g of x out front. So you will see things like this, and the instructions will say, you know, find d dx, find the derivative, or differentiate. So if we were to do that, we first have to recognize that the order is a little screwed up. That is, we've got the variable to the constant. So the first thing we're going to want to do is restate this and say, you know, this is the opposite of 1 to x squared, and then what would we have? Just the same old integrand, t to the 4th over 1, t squared plus 1 dt. Now, if we take the integral of that, if we take the derivative of that, the derivative of that is going to be the opposite of, and it's 1 to whatever, so the whatever is going to be raised to the 4th. In this case, it's x squared. If we raise it to the 4th, it'll end up being x to the 8th plus 1. And downstairs, the whatever is x squared, and we're going to square it again, so it's going to become x to the 4th, right? X to the 4th plus 1. And then we're going to multiply that by the derivative of the whatever. So we're going to say times 2x. So you might see this spelled out this way, minus 2x to the 9th minus, plus a 2x. I take that back. That's not going to be plus. It's going to be, the minus is going to be spread over both terms. So let's take that plus off of there. Let's get started again. It's going to equal a minus 2x to the 9th minus 2x. All of that, try it one more time. Minus 2x to the ninth minus a 2x divided by x to the fourth plus 1. And we are done. That is the derivative of this integral by the FTC. Thank you. I believe there is one more type of problem that we should look at that comes from this section. And it would be this kind of animal where we'd be asked to differentiate an integral, and notice that the limits both contain the variable. So how would we attack this guy? Well, it has to do with the fact that we can take any integral and split it or break it up. In this particular case, what we can say is, let's take this integral and start at radical x and go to 0 and work with t squared sine of 1 plus t squared dt, and then add to it, and now we want to start at 0 and complete it to 3x, and again it'll be t squared sine of 1 plus t squared dt. Now, what you might not appreciate right now, you will come to appreciate later. It really doesn't matter if 0 is between radical x and 3x. We can just choose any arbitrary number, 0, a negative number, a positive number, any number whatsoever will work, any constant. However, we just need to be mindful of the fact that choosing 0 makes for less work, or is the simplest number to work with. Now notice that this first one isn't of form. That is to say, the constant is not in the denominator. So we can simply take this one and turn it into the opposite of 0 to radical x, t squared sine of the quantity 1 plus t squared dt, and add to it from 0 to 3x t squared sine of the quantity, I'm running out of room here, 1 plus t squared dt. Now remember, we're going to differentiate. We're going to take derivatives now of this, right? So we're going to take and say, take the derivative of all of this, and the derivative of the integral, well, we'll say, geez, we're going from 0 to radical x. Well, we'll just put radical x in there and allow me to square it and to write the sine of 1 plus x squared. Now we have to multiply that by the derivative of radical x. And again, that's because of the chain rule. Working with this right side, won't it be plus now, putting in 3x and squaring it, won't that give us 9x squared times the sine of 1 plus 9x squared? And won't we have to multiply that by the derivative of 3x? So the final step might look like this. Let's adjust this a little bit. Radical x, of course, that's x to the 1/2. or 1/2 x to the minus 1/2, or 1 over x to the 1/2, or 1 over 2 times radical x, right? So I might start off with the positive quantity here, and the derivative of 3x, of course, is 3. So I might say the final answer is 3 times 9 is 27x squared, sine of the quantity 1 plus 9x squared. And then subtract, and remember what that derivative of radical x was. It was 1 over 2 radical x. So now maybe I can say that this is x squared over 2 radical x. And it's times what? The sine of 1 plus x squared. Now we could do a little more with that. We could write x to the 3/2 up top, but I don't know that that makes it any more elegant. So that brings a close to this particular section, that is part 1 of the fundamental theorem. Part 2 is something we'll talk about in class. The fundamental theorem part 2, as I mentioned way back at the beginning, it's something we've already been using. And it says, you know, if f is continuous on a closed interval, and suppose that big F is the antiderivative of f, then what does this mean? Well, it means, by the second part of the fundamental theorem, that's what it's called, we take the antiderivative and we say, let's evaluate it from b to a. In other words, put that upper limit in first and put the lower limit in, and then take the difference. This is what's often called the evaluation of a definite integral, or taking the difference of the antiderivatives. So we'll talk more about all this on Tuesday. That's all for now. Over and out.